Good morning. It's my pleasure to introduce Toby Gee, who's going to speak about the reduction modulo P of crystalline Mark Kisin modules.
Thanks. Thanks to the organizer. It's a pleasure to be here, pleasure to give this talk. This is about joint work in progress, very much in progress. Well, we have theorems, but we don't have all the theorems we would like to have, as I'll explain. But it seems like a good opportunity to talk about this work, even though it's not in final form. Okay, so the motivating problem is the following. I'm going to have K over QP, a finite unramified extension. Usually equals P. And I always write PK for the absolute Galois group. Okay, so choose a algebraic closure for this Galois group. And then I want to consider p-adic mod P representations. So for example, I can have a representation rho GK to then ZP bar. I'm going to write ZP bar for now. Really, you can just think that these are ZP valued representations. Any such representation factors through GLN of the ring of integers of a finite extension of ZP. So I won't worry too much about what the coefficients are. And let's assume that this is crystalline. I mean, you can talk about crystalline Galois representations. And then the question we want to address is, well, you have this representation, you can reduce it mod P and get a mod P representation rho bar, GLN, FP bar. And again, to imagine it's just going to GLN FP, it will factor through a finite image, a finite extension of FP. And the question is, what can we say about rho bar? Well, as stated, in this generality, you can say nothing because every rho bar, every mod P representation does in fact lift to some crystalline representation. But attached to the crystalline representation, you have some invariants, and in particular, you have the Hodge weights. So I want to say, what can you say about rho bar? Kind of in terms of the Hodge weights of rho. Okay, so I don't want to spend too much time on motivation for this question, or the original motivation, at least for me, but for a lot of people is that if you know things about this question, it tells you a lot about congruences between automorphic forms. So in particular, if you take n equals 2 and k is QP, then answering this question is basically equivalent to answering the question of when can you have congruences between modular forms of different weights. Come back to that a bit later. But so even if it's not immediately obvious this is an interesting question, it's an interesting question for a line answer for that. Let's do an example. Example of one-dimensional representations. And most of the talk, I'll take K for QP. Then rho is the character. Let me just try and do the same notation of my notes. So it's of the form, this is going to be an unramified character, and this will be a power of the cyclotomic character. So epsilon is the p-adic cyclotomic character. And lambda alpha is unramified. And lambda alpha for P is alpha. So alpha is some element of ZP cross. So let's set things up. And for this talk, I think I decided do the slightly unfashionable choice that the Hodge take weight of the 6 atomic character is going to be 1 rather than -1. Okay, well then, rho bar is sort of lambda alpha bar epsilon bar to the I. We often write omega with one p 6 atomic character. So this is just a character from GQP FP cross, describing the action on roots of unity. And since it's an FP cross valued character, and this is a cyclic group of order p-1, this character has order p-1. So this is lambda alpha bar omega to the I. And what this means is that, well, if you know your Hodge take weights, then you almost know what p reduction is. You know reduction on unramified twist, and you can't do any better than that. Feel free to twist this by unramified characters. And furthermore, this mod p Gauss representation, it depends on the Hodge take weight, but in fact, it only depends on the Hodge take weight mod p-1. So this kind of sort of knows, kind of it knows, and is determined by kind of the Hodge take weight of rho of p-1. Kind of all the data. Right, okay, so the picture for characters is very simple. That simplicity goes away completely, or almost completely, as soon as you go to the case of two-dimensional representations. So K is QP again, n equals 2. So in small weights, you can still say what's going on. How do I set this notation up? So let's let the kind of my notation for Hodge take weights is going to be HT of rho. So let's maybe now I have two numbers. Let's say there's 0 and h. I need to be 0. So this is not a completely general setting, but if I twist by a power of the cyclotomic character, I can make the smallest weight 0. So there's no loss of generality going on here. And in fact, if I make some unramified twist, I can also insist that the determinant of rho is, well, the determinant is a character with Hodge take weight h, and we just saw what those were, those unramified twists of the h power of the common character, so I can just insist that this is actually equal to epsilon to the h, epsilon unramified twist. And it turns out, and this is a very special fact to the case of k equals qp and n equals 2, that this is now not enough data to determine this representation, but it's enough up to one parameter. So well, slightly careful, rho is almost determined by a parameter which I will call AP, bar. And what is this parameter? If you know the classification of crystalline representations is in terms of Wheaty admissible modules, and this is the trace of the Frobenius on the modulus. This is the trace of the crystalline Frobenius. And the AP is supposed to be suggestive, because if I had a modular form of weight, I guess h plus 1, then with level prime to p, then I would be getting a Gauss representation of this kind, and the AP would be the usual AP.
Almost.
So yes, the one thing I was going to come to is what I mean by almost determined. If AP is a p-adic unit, which I'll discuss in a second, this representation is reducible, and then there's some different choices of lattice we could be making. Like the representation when you invert p is reducible, and then there's some ambiguity here. Maybe it's split, maybe it's not. But as soon as the valuation of this is positive, which is the kind of much more interesting and difficult case, then this is an irreducible representation, and then there is just a unique lattice.
In fact, it's a question I didn't have to ask. The residual representation is not very well defined if you look.
Right, well, here I fixed the lattice for myself to start with.
Fix the lattice.
So it is well defined.
But
yes,
not.
But here I'm not going to, and but it will actually still be, yeah, it will still be determined as long as the valuation here is positive. In a little bit, I will often semi-simplify the mod P representation, and it will be well determined. Okay, so yeah, so this has something to do with modular forms. So people studied this in the kind of 70s and 80s, and as I was just sort of saying, if the p-adic valuation is a unit, or equivalently with 0, equivalent if it's a unit, then the reduction is reducible. So rho bar is reducible, and I could tell you what it is exactly, but let me kind of sort of ignore the unramified part and just say that the restriction to inertia group is an extension of this mod P character by, sorry, the trivial character, but the mod P character to the power h. Yeah, so this is for modular forms, I think due to Deline and due to some combination of Fontaine and Serre, perhaps in this abstract setting. I'm not quite sure exactly what the history is. And then if so, that was valid for any h. But as soon as you're not a unit, things get much more complicated. Maybe the kind of the next case is that if h is between 0 and p, and valuation of AP is positive, then there's still kind of a simple formula. In this case, the reduction is irreducible, and irreducible representations have a pretty simple form. Maybe in fact I don't need to with my conventions. True to inertia, this is just induced from a quadratic unramified extension, which is true for all the irreducible representations, these are 10 representations, and there's this fundamental character of omega 2. So maybe I should just say that this omega 2 is kind of the character that's arising from, or via class field theory, it's arising from the character of GQP squared. And so I can write down a character of ZP squared star, and I just kind of reduce mod P and choose an embedding into F star. Okay, and the point is that this H here is the same H here. So in all of these examples so far, it's been a pretty simple kind of description of what's going on in inertia, and you can see that it's coming from the Hodge take weights. Okay, this fails completely as soon as you get beyond this range. It's already false when h is p plus 1. There's an extra possibility. And maybe I'll just sort of tell you kind of what happens in the next little range, and give one more remark before sort of moving on to some theory of how we might compute these things. So in this range, you get, maybe I now will just semi-simplify. So it's either one of the possibilities we already saw. So now for semi-simplifying, it could be this niveau 1 thing, that's the sum of the trivial and the 6 atomic to the h. It could be this induction of omega 2 to the h. That could still happen. It could also be the same induction, but now with translated by 1 minus p. Or similarly, there's an example here where I decrease this by 1 and increase this by 1. And in this range, Crystalline Breuil completely explicitly computed what these reductions are, including sort of the unramified part and everything in terms of this AP. but the answer is pretty complicated. So, for example, just to kind of show you this is a complicated question. If h is 2p, and you have to assume p is not 2, p is 2, then this is also equal to p squared, and somehow you'll feel like you're in a rather different range. Then rho bar is, so let's look at this case here. When does this happen? This h would be 2p, so I have 2p minus 1, which is actually just 1 mod p minus 1. So this is the case that, so I should restrict it to inertia here, and I can restrict it to inertia here. So this is equivalent to the condition that the p-adic valuation of ap squared plus p is at least 3 over 2. And maybe I won't write it down, but then you find that the kind of unramified twists here, you find that they're a root of a polynomial where you divide this, you then consider this divided by p times ap, which is a p-adic integer, and that's kind of the trace of the unramified part here. So that's maybe a formula that would have been pretty hard to guess, and it's quite hard to prove. And the expectation is that as h gets bigger and bigger and bigger, the answer just carries on getting more and more complicated. The formulas get more and more complicated. Various people over time, I think, have tried to kind of explicitly compute what happens in the range up to p squared. And what happens is sort of people get most of the way there and maybe give some talks about partial results. And then I think still no one has actually managed to completely determine these things. So the kind of lesson I take away from this is that trying to explicitly compute exactly what happens as a function of the representation is basically hopeless. I should also say that the fact that you can have a classification like this is very special for this case. I think I mentioned. In general, there would be some Hodge filtration data as well, and then how you would even encode that data is also a problem. But on the other hand, when you look at the sort of possible answers, it doesn't look so bad. Here, the kind of possible answers were very simple functions of the Hodge take weights, and here, I guess we had twice as many possibilities, but at least there's kind of some kind of formula. So it doesn't seem completely implausible that sort of computing all the possibilities over all the crystalline representations of some given Hodge take weights might be something you can do, even if you were given a specific representation, your chances would not be so good. Okay. Any questions so far? Yeah.
So for this case of h between p plus 1 and 2p.
Yeah.
So the last three possibilities occurs when h is
Yeah. Yeah. So I think yeah. So usual pattern is, I mean, if 2p behaves differently, but below 2p, sort of for p plus 1 to 2p minus 1, I think what happens is that when the valuation of AP is between 0 and 1, you get this. When it's bigger than 1, you get this, and then this occurs when the valuation is actually 1. There's some kind of picture with some annuli. Yeah. Yeah, I mean, there are a lot of results like this in the literature, and you can kind of see pictures of how this is happening as the weights go up. You kind of get, every time you add roughly p, you get an extra set of possibilities, and it's kind of tempting to think that there's some explicit thing going on, but it's not so clear that you can really do this. Okay, so sort of motivating thing to take away is that I'm motivated right now by trying to extract sort of what these possibilities are, sort of what these exponents are in these things from the Hodge take weights. That's something that would be nice to be able to do. Okay, so how can we do this? Well, let's move on and have some Breuil Kisin modules. Maybe I will try and use this board to put up a definition. So given the representation rho, and maybe I'll stick with QP for now. This is a crystalline representation. Well, a lattice in a crystalline representation, and maybe for now, I'll actually just write ZP out of laziness, but we could put some coefficients in. And let's just assume this is now n-dimensional So let's kind of assume that Hodge take weights of rho are kind of in the range 0 h. So I was trying to avoid this side of the board, but maybe that's actually the side that's good. Okay, well then, by work of Mark, I guess, attached to rho is a rank n Breuil module. Which Breuil modules will be denoted by we've got again. But what is this? Well, probably many of you know, but let me just recall the definition. So to determine this data, this assignment depends on a choice. So we choose pi, our favorite uniformizer, for QP. So you probably a couple of obvious choices, but let me use that notation. Let's have E of U for the minimal polynomial pi, and also fix compatible system of p power roots of pi in QP bar. So this kind of assignment depends on those choices. But then this data is, this M is something pretty simple. So M is a free rank n module.
All right, E of U is just x minus pi, no?
Yeah, exactly. I'm just writing it this way because in case later on I want to do something in a more general context, which I may do, and then yeah. I mean, you might well take your unifiers to be p or minus p, and so probably it's u plus or minus p. We're also frequently going to be mod p, and then so this is a free module over a power series ring PPU, which has Frobenius given by U is used for P. It's not just, I mean, a free module would not be enough data to capture very much, but there's also, it's equipped with a semi-linear Frobenius. So also doing it to be, this is semi-linear. And the cokernel of the linearized Frobenius, I'm going to write a capital Phi P up to star, M is the Frobenius pullback of M. Phi induces a map on this, and I insist that the cokernel of Phi, cokernel of capital Phi, is killed by minimal polynomial E of U to the power h. So I made this assumption the Hodge take weights between 0 and h. Again, h was positive. And so, again, I can always make that assumption after some cyclotomic twist. I'm going to do that. Okay, so you have this assignment. This is some functor. I should say that not every Breuil module comes from a crystalline representation, but that's not going to be too important for us. What is important for us is that these are some rather more sort of hands-on gadgets than having lattices and crystalline representations. And they do know something. They know a lot about the Galois representation. This doesn't completely determine it, but what you can determine, at the very least, is that M determines the Galois representation restricted to QP adjoined by compatible roots of the parameter pi. So if you've never thought about it before, it's not so clear how much data I might be losing here. In fact, none at all in some sense. Restriction of a crystalline representation to this extension is fully faithful. But more concretely, if you think about what happens in mod P, if you look at semi-simple representations, these are tame, and this is a wild extension, so you actually lose no information. So in particular, it determines row bar semi-simplified, and yeah, that's all I want to say. So it's row bar.
I'm sorry, I didn't understand the argument here.
The argument is just that these the semi-simple representations are all kind of generalizations of this kind of thing. They're all direct sums of things induced from these fundamental characters. And those are coming cut out by tame extensions, and this is this wild pro-P extension. So on the semi-simple things, you don't lose anything more P. You can make this more precise. What you're really using is the Schroeder extension of the trivial and cyclotomic characters corresponding to this choice. So you can really check that that's all you're losing. But in particular, it's just some extensions between sort of cyclotomic twists, and so on the same simplification, you're losing nothing.
Sure, I can ask.
Yes.
Just slightly confused, but is it covariant or contravariant?
I mean, I think it could be either at the moment. The way I don't think I've given enough.
I mean, M is effective, right? Here.
Yeah. Yes. I mean, I could also done some twist and some dual. And
You answer
And I'll
that
tell
question,
you-
then you have to think about what your choice for Hodge tape weights.
exactly.
It's a choice of
I did make a choice up there.
Okay.
What I will do in a second is tell you what my convention's amounting to for Breuil Kisin twists, and then if you could.
I also have another stupid question.
Yes.
Gray is not working, but where does the dependence apply to the 1/p infinity come in?
I mean,
I don't understand the P, because I mean, the residual representation might have order divisible by P. I mean, rank 1 it cannot, but otherwise it could. So,
I mean, not the semi-simple.
Uh,
Not the semi-simple, not the semi-simplification.
I mean, a rank 2 representation might have order divisible by irreducible representation might have order divisible by P. I mean, rank 1 it cannot be, but
I don't think so. I mean,
okay.
like, because
Say,
it's factoring through this tame part. I mean, like the rank 2 ones literally come from this construction, and in particular the P part.
and for a character, yeah, but you don't have character as a residual representation.
These, I mean, I'm saying every irreducible rank 2 representation.
Rank 2, you are in the rank 2.
So this is a rank 2
Okay,
representation.
so now you
And
understand.
similarly in rank n, they're all the irreducible objects are just coming from.
So, but I mean, isn't it the case that sometimes your residual representation is absolutely irreducible?
Yes.
But they're still all inductions of characters, the reducible ones.
Yeah. Well, I don't want to interrupt you.
Yeah, I'm happy to talk about it afterwards.
Yeah.
Maybe I should.
Sure.
Yeah, so my example, and I mean, hopefully I'm not going to find that if I try to make my life easy and choose +1, I've made some inconsistency. But the kind of n equals 1 case, these twists of powers of the cyclotomic character correspond to a rank 1 module. So maybe M is CPU times some generator E. So this is just the generator for this rank 1 module. And the Frobenius is given by alpha times. Now there actually really is a chance that I've got some inconsistency here, because I know I've not told you enough to pin me down, so it's okay. I didn't say which Frobenius I was using. So it's just given by this rank 1 thing here. And so in particular, you can kind of see it's got a very simple shape, and integer I is the same, probably like I was H. I did, but just stick with I as I've written on the board. And I'm going to write M bar for the reduction mod P. So this is given by P of E is alpha u to the I P. And if we compare to the mod P Galois representation, I guess this is now, sorry, alpha bar representation, producing mod P, you can see it's basically the same thing, except I've retained slightly more information. Because here I knew this I mod P minus 1, and here I is still an integer. There's no kind of congruence condition here. So the mod P Breuil Kisin module knows at least as much information as the Galois representation, so as the semi-simple Galois representation, and in fact it's kept track of rather more, it's kept track of the Hodge-Tate weight, literally. So that's kind of nice. And furthermore, while it's kind of not so easy to classify these integral Breuil Kisin modules over ZP, mod P, it's actually pretty simple to see that these are all things there are, because you're having some rank 1 module over now FP double brackets U, and you've got the Frobenius, and the Frobenius is going to be determined what it does on the generator, and all it can be doing is multiplying by something times the power of U. In principle, you could have some now multiplied by some unit in the ring, but it's easy to check that when you change variables, you can really get down to an exact power. So it's kind of a fun exercise if you haven't done it to see that all the rank 1 things mod P are just of this form. So now, if you kind of want to determine, like, if you want to prove results like this, you could try and think, well, we can now write down what rank 2 mod P Breuil Kisin modules look like. This is again some kind of linear algebra-like data. And then you just have to work out how the Hodge-Tate weights of the original representation rho are turning into information of this kind, turning into something about these experts. And of course, the answer can't be completely simple because we already saw here that there are multiple possibilities. So it's not just like this GR1 case. There has to be some kind of connection. And our main result is giving you an example of some connection between Hodge-Tate weights and the mod P Breuil Kisin modules. So maybe I'm just going to now try and state our result. First of all, I have to state a result due to Brandon Nevin and Carl Erickson. They were the first people to consider the invariance 312. So they have a definition. They say that the Hodge type of a mod P Breuil Kisin module n bar, it's just an n-tuple of integers that's a multi-set, they may have repeated integers, of the elementary divisors of the co-kernel of this linearized Frobenius. I guess I should kind of indicate that it's for M bar. So what does that mean concretely in this rank 1 case? It just means this integer I. In general, what happens is the co-kernel, by the assumption over there, the co-kernel is killed by some power of U, this usually H. So you're looking at a finite module over sort of the ring FP U, using mod U to the H, and you're just writing down so this is now a sum of cyclic modules, and you're just writing down the lengths of those modules. So that's some invariant. And they made an observation about the connection between this invariant and the Hodge-Tate weights. Follows. let me also write maybe HT of rho, just to be explicit, is the multi-set also of cardinality n, and my rank, of Hodge take weights of rho. And maybe this guy I'm going to call Hodge, then graph, this set. And for stating this result, let's write the Hodge take weights as H1, Hn, and Hodge invariant as A1, An, and I want to write these as dominant co-characters. So I want to insist that Hi is Hi plus 1 and Ai plus 1 for all I. So, in decreasing order. And then kind of proposition. Ericsson is that the Hodge take weights are at least a Hodge type in the sense of the Breuil order. So that means that kind of all the partial sums here are at least the partial sums here, and the total sum is equal. So I'm a I equals 1 for j, hi is at least some I equals j, ai with equality. I'll say something slightly more in a bit about how you can see the Hodge filtration on the characteristic 0 or the integral Breuil Kisin module M, and then this statement is some semi-continuity statement. Yes.
Is there any way to read off the Hodge type of M bar, like from rho bar semi-simple directly without passing the Breuil Kisin module, or not really?
Not really, because you can see here that you would be in trouble because you could only at best do I mod p minus 1. So yeah, so there's the mod p Breuil Kisin module knows a lot more than the Galois notation for this computation. Yeah, so this is kind of natural statement you can get. We actually proved this as well for semi-stable representations, and there I think this result is basically best possible because already, in fact, if I was doing semi-stable things, already it turns out that for any small values of h even, I can see more possibilities in this. I can already sort of see any kind of semi-simplification for semi-stable representations, even if the Hodge take weights are sort of 0 and 3 or something with p very large. The only constraint on them is basically this constraint. But in the crystalline case, this is obviously not kind of the best possible result, because if it was, then we'd see a lot more representations up there. Okay, so what's our theorem? Our theorem today is congruence. So this set of Hodge take numbers is congruent, and I'll explain in what sense I mean. Just a moment for the Hodge numbers. So I'm now not meaning in the strong sense that I've ordered them. All I mean is that you reduce this set mod p, you reduce this set mod p, you have some now multiple elements of fp, and I'm just saying those multi-sets with their multiplicities for the same. Okay, so a nice exercise is to see just from this, which maybe I'll just explain in 1 second, is that this, for example, actually predicts these kind of possibilities up here. And so maybe I should explain that. If n equals 2, and the Hodge take weights of rho are kind of in the setting I had above, 0 and h, then what I'm saying is that the Hodge things have to be congruent to this mod P. And so maybe let's do the case that sort of P plus 1 less than or equal to H less than 2P. So I have to have two integers congruent to 0 and to H mod P. And also from here, I know that they have to sort of between 0 and H and add up to H. So the only possibilities for the Hodge are well, 0 and H, or H minus P and P. Yeah, you can see that I'm not making some claim about the orderings because in this range, this is less than or equal to this. So it's not the case that the biggest one is. But those are the only two possibilities. And if you now look, for example, at these kind of, if you had a reducible representation, then on inertia, you'd be getting omega to the H plus 1. And here you'd be getting omega to the H minus P, omega to the P. And because omega has order P minus 1, this is omega to the H minus 1. So it is at least consistent with the above, but in fact, furthermore, it even predicts the above.
For this, are you assuming rho is crystalline?
Yes, sorry. This one, throughout this talk, rho is crystalline, apart from in the aside I made about semi-stable representations here. So rho is crystalline. Thanks. Yeah. So I should say that we haven't checked the details, but I think we are reasonably optimistic of proving a version for sort of split reductive groups as well. And I mean, this statement is okay, and it's proved in this generality already by Brandon and Carl. And here, the statement becomes that you're in the same orbit under the action of the affine Breuil group. And maybe I won't kind of write that out in detail, but we expect to be able to prove that as well, of corresponding statements. Okay, so one remark is that I already did something slightly dubious here when I made this claim. That you could see that these were the possibilities, which is, as I then mentioned, when I take my rho and reduce it mod P, there's no reason that that should be semi-simple. And the formation of this invariant doesn't necessarily respect semi-simplification. I mean, like, it's actually a thing that happens is that for these reducible things up here, maybe the mod P for a Kisin module maybe has a matrix of Frobenius that looks something like this. And then the Hodge type of this is always kind of 0 and H. But when I semi-simplify, sorry, that maybe make a more general point, you could just have something like this. You always have 0 and H, no matter what these powers are. But of course, if you semi-simplify it, you get something that might not have the same invariant. But in fact, it's easy to check that if you have a Breuil-Kisin module giving rise to a semi-simple representation, the Breuil-Kisin module needn't itself be semi-simple, but the semi-simplification also occurs in this way, and the theorem applies there. So in fact, you get sort of more information, you get the invariants for this matrix, and also for the sort of semi-simple matrix. So that's good.
Matrix for Frobenius?
Yes. Yeah. It's probably, yeah, should be slightly careful, but that illustrates the point, at least. I mean, I think these ones down here, the non-split things, really do look like sort of this kind of thing is really a thing that happens. So kind of natural question to ask, I kind of said this result wasn't the best possible thing in that there were plenty of kind of sets of integers that satisfied this inequality but didn't actually occur. You can then ask, if you put in this extra condition, what's the situation? And the basic answer is we don't have a clue. In some sense, it's I don't know of any examples of kind of sets, sets that are allowed by these constraints and don't occur. But on the other hand, I don't have a good supply of, even for the GL2 situation, I don't really know if I take Hodge weights sort of 0 and something big compared to P, I don't know what the Breuil modules actually are. You can kind of see that up to about Hodge sort of 0 and up to about P squared, looking at the Galois representations tells you that you pretty much have to see all of these possibilities. And that makes me kind of optimistic that maybe it's actually the correct answer. But it's kind of, I don't think we really have a technique at the moment. We have, say this is work in progress, we haven't talked very much about some kind of converse, but yeah, I think I'm somewhat optimistic that this is the best possible in this setting, but I'm certainly not going to claim to have any idea how to prove that. You can also ask, I don't know how to compute mod p-Breuil Kisin modules so well that actually come from particular crystalline representations. But we do know actually quite a lot about the reduction of the Galois representations, just the actual Galois representation, not the Breuil Kisin module. And in particular for this GL2 kind of QP example, the way that Breuil made this calculation was using the p-adic Langlands correspondence for GL2 QP. And using that, you can actually do computations in all weights for the Galois representations and see exactly what the possibilities are. You can even do the kind of non-semi-simple possibilities. And those, even the non-semi-simple ones, exactly agree with the ones that we predict from this. So I take that as a somewhat encouraging sign. I won't kind of maybe write stuff in the interest of saying a tiny bit about the proof, but the way you can kind of, without invoking the whole p-adic Langlands machinery, the kind of way that you can reality check this prediction is using congruence between modular forms. The basic point being that if you take some modular form of low weight, then it's actually kind of easy to produce congruences to higher weight just purely from sort of group theoretic information. So that's like one sentence. So by kind of Shimura, sort of mod p modular forms of weight k, so sort of weight k modular forms have something to do with the cohomology of GL2FP acting on k minus 2 FP squared. And for kind of small values of k up to p plus 1, this is an irreducible representation. And so now if you take some other very large value of k, for which this is a Jordan-Holder factor, then just thinking about what Shimura tells you, you get a congruence between modular forms of some low weight and some high weight. And so in particular, that means that all the representations that occur in the low weight also occur in the high weight. And you can make this into a kind of explicit recipe that sort of by induction gives you a lower bound on the set of Galois representations that occur. This gives you an upper bound, and you can kind of just check that they agree. So that's kind of for GL2. I'm going to just make one remark about a natural question then is, well, do people know things about what happens for GLN? And there is some information. So for kind of the GLN, the question of what sort of things you have, at least in small weights, has something to do with the weight part of Serre's conjecture. I'm not going to go into it in detail at all, but there's no, as far as I know, explicit prediction for exactly what the reductions mod p even for GL3 are. But you could, if I now say here's a representation with Hodge weights sort of 0, p and 10p plus 1 or something, it's now an exercise to just use this and get at least an upper bound on the possible semi-simple representations. And using kind of results in the literature, you can then try and get a lower bound in a similar kind of way. And in all cases that I've checked, the two bounds agree. I mean, in principle, it should be possible for GL3 to really precisely determine what's going on, but I'm not very good at combinatorics and it's work in progress. So I'm kind of optimistic about having checked. But the most interesting thing is that even for GL3, there's not an explicit conjecture in all cases. So Florian Herzig made a conjecture in sort of so-called generic range, which basically amounts to sort of having all of the gaps between these weights be sort of a bit smaller than p and a bit bigger than 0. And similarly, the kind of Galois representations, you want all of these exponents to be sort of not close to 0 and p minus 1. And in that case, you can check that for GLN and even over an arbitrary unramified field, we have a similar result with a very similar proof when wherever k is unramified. You can check that what we predict exactly agrees with what Florian has in the generic setting. And for GL3, there's a paper of me and Florian and Dave Savitz. We made some kind of explicit prediction for the kind of semi-simple reductions in some kind of low weight settings, but with no genericity hypothesis. But the method was extremely ad hoc. If you look in the paper, there's kind of obvious weights, shadow weights, shifted weights, and obscure weights, I think, and they're all just from different combinatorial recipes where, I mean, my memory is that over the years, maybe we've written everything down, then we've realized that there was something else that we had to find. But anyway, if you then kind of chase through these various somewhat laborious constructions, if you then just compare them to what we have here, they completely agree. But here you can just immediately write them down. So I don't want to make it a conjecture, but I think it's a definite possibility that this actually gives you a very explicit, simple combinatorial recipe that completely predicts the semi-simple reductions of crystalline representations to QP in n dimensions, which would be quite nice because as far as I know, I mean, maybe it's too good to be true because as far as I know, no one kind of had suspected there was such a recipe, and this recipe is very simple, but it does seem to work. Maybe the one other remark I make about this is that, interestingly, this is again sort of work in progress, it doesn't give you the right answer. It doesn't give you a tight upper bound. If you do QP squared already, even GL2 QP squared. But the kind of issue that comes is if you do things where now you have sort of Hodge take weights that maybe sort of 2 embeddings, maybe I'll sort of call them tau 0 and tau 1 from QP squared into QP bar. And the kind of behavior that's bad is if you have something like the Hodge take weights here are 0 and 1, and here sort of 0 and something bigger than 2p, so 2p or more. So when the weights here are extremely different, you can easily see that this is not the best possible result. But on the other hand, I have some kind of ideas about what might be going on, so I'm not going to rule out that there's a completely explicit answer here as well. And this kind of possibility doesn't occur in this sort of low part of Sayre's conjecture. It's still good there. Right, I think that's enough examples, and I'm just going to spend 5 minutes on the proof, which in some sense is pretty short. So let me
ask a question.
Yes.
Can you explain a little bit why things goes wrong in this case? Why you cannot get this on?
This case is just an exercise. I mean, just do, and maybe I should make it some 3p to be completely safe. Think about what Breuil tells you. Like just take the representation, it's like sim 0 of this, tensor sim 3p minus 1 here. Compute what the Jordan-Holder factors are. There are not very many. And you find a contradiction. When you don't find a contradiction, you find not all these possibilities occur. And even kind of simpler example, I like this kind of regular weight thing, but if I made both the weights 0 here, then already Fontaine and Phi, and then extended by Robin Bartlett, kind of proved that the reductions are kind of exactly the simplest thing they could be. Fontaine and Phi theory sort of works if you're 0 in all but one place, and then you're kind of Q in the remaining place. So yeah, so it's not so hard to see. It just can't be true. But it really does depend on, I think the failure really is depending on the weights being very different. Okay, maybe I should very briefly explain the proof. So what I first say will also something about this result of Brandon and Carl's. So you can define a filtration the Nygaard filtration on the Frobenius pullback, is just the elements here. So you have the linearized Frobenius takes x into the notation p of u to the I. Pullback of the p of u-adic filtration.
That's the upper star of that.
Yes, it is. I was thinking it looks slightly strange, but I couldn't place it. Thank you. So yeah, so it's a filtration on p upper star, then decreasing filtration. And a result, again, I'm not totally sure who to attribute things to, but I think maybe a combination of Crystalline Breuil and Tong Yu tells you that the graded pieces of this are free TP modules of rank. Well, it's the rank of the kind of the graded pieces for the drum filtration. Maybe on QP bar of P. I mean, it's saying more than this. It's really the result is that when you invert P, this filtration agrees with the filtration here. But in particular, these are just determined by the Hodge take weights. It's something like the sum of the number of Hodge take weights less or equal to I. So this filtration knows about the Hodge take weights. And you can now imagine how you can kind of get something here, because when you reduce mod P, there's some semi-continuity on how this filtration behaves. And so that's how this result at the top comes. You can also do the same kind of game when you reduce mod P. So maybe I'm going to call this phi sat. The upper star m bar is the same definition. So let me just put it with m bar. And when you reduce this filtration mod P, you're going to be contained in this one, but this one could be bigger a priori if you think about it. So, okay, actually just stay in the middle. Right way up. Okay, so I just want to make a definition. If m lower dot, this is my indexing, is a graded, I guess, finite dimensional empty vector space. I want to let Wm be the function from Z to Z that takes the integer I to the dimension of the ith piece minus the dimension I minus first piece. Okay, so what's the point of this definition? We have a kind of easy lemma, which is basically just from the definition, relates our two invariants, doesn't like this. So if I apply this to the, if I take the graded piece for the Nygaard filtration and then reduce mod P, this dot, this I is the multiplicity of the integer I in the set of Hodge take weights. So that just follows from this also Breuil mu. And if on the other hand I apply it to the gradient of this saturated version, then again I get multiplicity of I in something, and this time it's in Hodge. Again, that just follows by putting this thing in Smith normal form or whatever and reading off the integers. Okay, and so it's kind of as follows. So from M, or rather, perhaps better, from rho, rather than just the data of this Breuil-Kisin module with its Nygaard filtration, you actually have an actual F gauge, so some kind of coherent sheaf, some sheaf on its stat EP sin of Argov and Jacob and Drinfeld. I'm kind of guessing the next talk will say more about this, and as I'm out of time, I'm going to say very little. And you can reduce this mod P, and you get something E bar. And then there's also something maybe I can call E bar saturated, which is the thing that corresponds to this guy. And so really, now we're just trying to study something about the difference between these two things. And it turns out that the cokine of this is something very small, the same Breuil-Kisin module here, so there's not much room for anything apart from the filtrations to change. And so I guess if I now take the cone of this, I get something on the kind of something's called the mod P Hodge stat. And a coherent sheaf on here is something very simple. I'm almost there, don't worry. It's just a module for the kind of usual Bayes algebra. It's a finite dimensional module for this algebra where you have the usual relation, usual kind of commutation relation between these. So it's a module. But you've taken yes, sorry, it's a graded. You're right. That's T, and degree of T plus 1 and d by dt minus 1. And now it's an elementary exercise to check that the irreducible modules for this are just of length P given by, you have some generator and sort of T puts you up a degree times d by dt takes you down. And for such a module, if you think about what happens here, it doesn't change these functions modulo P. It doesn't change, if you like, the function where you add up the values in the residue class mod P doesn't change. So those two quantities are the same for both of these. And here you see where these are. So
You have two different meaning for T.
yeah, sorry. I think the notation, yeah, sometimes means
Maybe U. Oh, okay. Well,
U is kind of a bad idea as well.
no, for the other T.
Yeah, excellent. There's a U and a T in Bargov's notes, for example, but there's also a U in Breuil-Kisin modules, which is maybe less good. I'd better stop because I'm like 3 minutes over. So.
How much of what you said here carries over to an arbitrary finite or ramified extension?
Unramified extensions, you basically get the same thing. There's kind of an obvious statement where you have coefficients and embeddings and you just get the same statement with the same proof. Ramified extensions we haven't thought about. I imagine there's something, but it's, if you think about it for a moment, you can see that it's, if you just try and do the same argument, you're going to lose quite a lot of information. I should just say, by the way, that I meant to say, but I was running out of time, that we had some help with this. So in fact, I remember Mark giving a talk about 20 years ago. He explained that when you got to a certain point in an argument, and then he had to employ a technique in algebraic geometry, a well-known technique, which was asking over Gabor for help. And here we kind of reduced to some kind of situation where we had this kind of thing, and we employed the technique of asking Jacob for help, and it was equally effective. Yeah, I mean, I would say in some sense that this result was harder to find the statement of than the proof, but since we didn't entirely find the proof ourselves, I think that would be unfair. But I think it genuinely is, once you know the statement, and particularly if you know that it can be proved in some way using ZP sin, then the proof is not so hard. But yeah, finding the statement. I mean, we could have found the statement 20 years ago, but I don't think anyone. Of course, if someone out there knew this statement before, then please tell me. But yeah.
Yes, how should I think about this? Of the geometry of the stack. Cost.
I mean, I think it's. Am I right that there's some small part in this? Like everything is going on at this kind of mysterious point of the stack. That's the one you don't just see for free. And I think this is a manifestation of you having like a B mu P or something at some point. Is that right? Or
I think like the stabilizer close point is GA sharp semi-direct product GM, but the action is weight P. And that's where this comes from. So any such sheet is going to be filtered by things supported on this, and the weights have to go up by. But that code is a cokernel, right? I mean, this is all happening at the BOM level. I mean, it's injected, sorry.
yes, well, I think. Yeah, and maybe I got confused about this at some point about. Yeah, you're probably right. I want to just be cautious because. Yeah.
So from rho, you can construct this E, which is a coherent shift on this ZP sin stack. What is the E bar and the E bar stack?
Sorry, yeah. The E bar is just tensoring with FP, and this is kind of the operation that replaces the kind of filtration we had here by the saturation. You can, I think, formulate that in a more commutative algebra way. Maybe it's like a Cohen-Macaulay hole or something, but
it's like a
reflexive hole.
Yeah.
Yeah. So this is using. I mean, this F gauge is some reflexive sheaf, and again, you can see this in Bargov's notes. It's kind of a refinement of the Bargov-Peters theorem that from these you have prismatic F crystals. Some more data. I should just make one more. I think it's plausible that you can actually prove this in more classical language using back modules or something, like making this explicit with the Q-Duran prism, but we haven't tried very hard. Yeah, sure.
Oh, you mentioned wave particle conjecture. Could you explain like how this prediction can add add something to a parse?
I mean, it's just that from this prediction, if I tell you some Hodge take weights, you can write down upper bounds on the sets of reductions of those crystalline representations. And so it's some kind of result in the kind of elimination direction, if you like. But in particular, this result has nothing about hypothesis on the size of these things or any regularity hypothesis. So it makes a prediction. Of course, you don't know if that prediction is any good, but it seems remarkably good in practice.
Okay, let's thank Toby again.